So in the second part of this lecture, I'm going to look at what's commonly known as itinerant magnetism. Okay, so that's magnetism from, instead of having localized magnetic moments, as in Curie magnetism, um, itinerant means electrons that are able to move throughout the material. Okay, so we're thinking about why certain metals, typically the 3D metals, iron, nickel, and cobalt, why those metals are paramagnetic, sorry, are ferromagnetic. Okay, iron, nickel, and cobalt can form permanent magnets. Okay, so first of all, I just want to remind you about transition metal band structures and density of states. Okay, so a typical transition metal will have a band structure that looks schematically something like this. Okay, so these are the D bands, and the red is the S bands. Okay, and there were 5 of those and 1 of those. Okay, to fit in with the number of S states and the number of D states. So that is my very crude schematic of a transition metal 3D band structure. Okay, so what we have is the S states are very much more delocalized in the material, so they are very much like a free electron gas, so they're very parabolic. Okay, the D states, the d orbitals, are much more localized in a material. Okay, and localized states means bands that are very flat. Okay, if you remember about tight binding and you remember about the overlap integral, this beta parameter, beta is a measure of the bandwidth. Okay, so the D bands have a very small beta, the S bands would have a very large beta. Okay, that's also, beta is also what we sometimes call the hopping parameter, so the probability of an electron hopping from one site to the next. Okay, as I said, D state's very localized, so small hopping probability. Okay, so there we have our typical transition metal band structure. Now here's a real band structure, or should I probably say this is a calculated band structure for copper. Okay, and we can see the similar features here. So this is very parabolic here, and in fact you can kind of trace a kind of parabolic band that does something like this, gets hybridized around these regions, and we've got a set of D states around here that are quite flat. Okay, and if we count carefully, 1, 2, 3, 4, 5, there are indeed 5. Okay, now it's copper, so we know that the electronic configuration of copper is 4s1 3d10, which is telling us that the copper D states should all be occupied. Well, this dotted line here is the Fermi energy, and you can see for sure that all of the D states lie below the Fermi energy. Okay, so that's my schematic of a density of a band structure. What about the density of states? Well, it's possible to sort of superimpose this in 2 parts. So if we thought about the S first of all, okay, so this is density of states here. This is energy. Well, the S state is quite parabolic. It's quite free electron-like. So probably we're going to expect something that looks a bit like that. Okay, it goes as the square root. So this is the S state. What about the D states? Well, if the bands are very flat, it means that if I pick an energy here, there are going to be a lot of states that satisfy that energy. So it means that the this energy range is quite small, but the density of states there will be quite high. And I could draw that schematically as something like that. Okay, so what we might imagine is the total density of states. So this was D, and the total density of states we might draw as just the superposition of these two things, something like that, with something like that. Okay, it's quite a crude the representation of the uh, of a density of states, which can actually be, as we'll see, has lots of features in it. But basically, all transition metals look. The density of states can be interpreted in this fairly simple way. Okay, so that's a little bit of background information that we needed. Okay, so why should some metals be ferromagnetic? Why should they have a spontaneous magnetization? Well, it comes down to the idea about exchange. Okay, exactly like it did for the localized spins. Okay, and we can imagine two scenarios. So I'm going to draw pictures of density of states versus energy. So this is versus energy, and I'm only going to focus on the d states, okay, because the d states they've got potentially 5 different electrons, well 10 electrons if we include spin, and so it's going to be the interactions between those electrons that are going to drive the magnetism. Okay, the s states, there's only 2 electrons there, they're going to be opposite spin. We couldn't have 2 electrons with the same spin. There's no mechanism to do that. So the S states are not going to be responsible for creating any ferromagnetism. So we can just focus on the D. And we could have 2 scenarios. So we could have the case that, so let me draw a mirrored density of states. So for example, this is magnetic moment pointing up, and this is magnetic moment pointing down. Okay, and in this paramagnetic state, the ups and the downs are paired, and we might have a Fermi energy EF. Okay, and what that would mean would be we'd occupy all these states, and we'd occupy all those ones. Okay, and this is so this would have no magnetism. Okay, but if we thought about the exchange energy, that would be high in this system. Okay, how could we lower the exchange energy? Well, again, if we have more states where the spins are aligned, that would lower the exchange energy. So there's another possible scenario, and if I include the exchange energy, what could happen is I would lower the energy of these states, and I would raise the energy of these ones. Okay, and so potentially now, if I put in EF, I've got the same total number of electrons occupied, but this is magnetic. Okay, so this would have more upspin, up magnetic moments than down magnetic moments. Okay, this is very reminiscent of what we saw for the Pauli paramagnetism, but remember, there's no field applied. Okay, so no external field applied here. It's almost as if the exchange field is acting like an internal magnetic field, okay, to drive this polarization. Okay, so what this would mean is this has a lower exchange energy. Okay, now that can't be the only factor, because if that was the only case, all materials, all of these transition metals would become magnetic, and we know from the first row only iron, nickel, and cobalt are magnetic. What's tensioning against this is actually the kinetic energy of the electrons, and so uh, this has low kinetic energy for the electrons, and this one has high kinetic energy for the electrons. So whether we find ourselves in this situation or this situation is just a balance between the exchange energy and the kinetic energy. How do we determine which of those are which one dominates? Well, a man called Edward Stoner came up with the idea, and it proposed a criterion, and it's about the so the Stoner criterion is that a large density of states at the Fermi energy means the exchange energy dominates. Okay, now that again has some questions. How large is large? But what we can often do is rationalize. So what we're able to do is, for example, make a measurement, or we can do a calculation and see which system has the lower energy. And if we want to understand why one becomes ferromagnetic, we can normally relate it back to the fact that the density of states is particularly large at the Fermi energy. Let me illustrate that with some real examples. Okay, what I'm going to show you now are a set of densities of states, and they're calculated densities of states. They're done using something called density functional theory, which you'll learn about in the third year modeling course with me. And essentially, that's a way of solving the Schrodinger equation quite accurately using computers. Okay, these calculations are actually fairly trivial. They ran on a small PC. So what have we got? First of all, we've got copper. Okay, remember this is 4s1 3d10, and here is its density of states. And if you like, the red is up and the blue is down. Okay. Now copper is diamagnetic. Overall, there's the Pauli effect, there's the Langevin diamagnetic effect, and the diamagnetic effect wins out, so it's a diamagnet overall. Okay, but we can see why the Stoner criteria would not be satisfied here, because all of the 3D states which give rise to the large DOS, okay, these large features here, are way below the Fermi energy. Okay, so the dotted line here is the Fermi energy. So the value of the density of states at the Fermi energy is low. So the Stoner criterion is not satisfied. So there's no exchange doesn't dominate, the kinetic energy dominates, and there's a sort of perfect mirroring between every spin up is paired with an equivalent spin down. Okay, so that is copper. Okay, so in titanium, the electronic configuration is 4s2 3d2. Okay, so we get a very similar profile of the density of states, where we've got some sort of, there's a low S background, and then there's a high series of peaks which come from the D states. It's only 3d2, so only 2 of the 10 d electrons are occupied, and so the Fermi energy sits very much within this set of D states. Okay, so these ones down here correspond to occupied, these ones correspond to empty, and the Stoner criterion is not satisfied. So titanium is paramagnetic overall. There is no exchange, doesn't dominate. And you can see why, because the Fermi energy actually lies in a dip in the density of states. Okay, so the density of states there at the Fermi energy is higher than it was in copper, but it is still low. So titanium um, uh, is not ferromagnetic. Okay, what about iron? So this is a calculation on iron in the paramagnetic state. So I've not allowed any splitting between the between the up and the down. Okay, so again these are up, and this is down. And remember, iron is 3D. 1, 2, 3, 4, 5, 6. Counting off a periodic table there. 3D6. Okay, 4s2, 3d6. So again, the Fermi energy is within the set of D states, but it doesn't. But it's further up than titanium. And you notice straight away the value of the density of states at the Fermi energy is high. Okay, it's about as high as it could be. Okay, so in this case, the Stoner criteria is satisfied, and this system could lower its energy if we allowed the exchange splitting to lower the red states, and so occupy to have more electrons with their magnetic moments in one direction than the other direction. Okay, so this is a calculation having done that, and you can see, well, a few things from here. So let's see what to notice. So this is the Fermi energy here. You can see that there's actually sort of uniform shift. So I've got big peak, smaller peak, big peak, smaller peak, smaller peak. So the difference in energy between this peak and this peak is it's probably about 5 eV. So that's the value of the exchange splitting. Okay. And so what's happened is we've essentially moved the blue states this way, and we've moved the red states this way. So the number of upspins, number of red ones, is greater than the number of blue, because this area under here is clearly bigger than the area down here. So there are more of these electrons with the magnetic moment pointing this way than there are with the magnetic moment pointing that way. Okay, so the high density of states at the Fermi energy has basically driven iron to lower its energy and become ferromagnetic. Okay, so here's a summary of that. So if we were to calculate these areas, we could work out the net difference between the number of red electrons, the up electrons, and the down electrons, and it's about 2.15. And that's quite interesting, because if we were to measure the magnetism of iron, we would have per unit cell a value of the magnetic moment of about 2.22 mu b. Okay, so what this is saying is, so each electron provides about mu b's worth of magnetism. So you can see a few things here. First of all, that the kind of spin of the electron, the magnetic moment due to the spin of the electron, pretty much accounts for the observed magnetic moment in iron. So the magnetism of iron is almost completely, to within a couple of percent, coming from the spin angular momentum of the electrons. The contribution from any orbital motion is actually 1 or 2%. Okay, it's really quite small. The other thing to notice is that, of course, in the Curie approach to paramagnetism and ferromagnetism, when we had localized moments, we always had an integer number of electrons that were contributing to the magnetic moment. What we found here is we've got a non-integer, 2.15. Okay, so because these are itinerant electrons, they're distributed, we don't have to have an integer number of electrons corresponding to the magnetic moment. Okay, so that's quite interesting, and some of the formulas that we have, for example, for domain boundaries, all of those things still work out. We just have to put in non-integer numbers of electrons. Okay. Just to say something else that came out from these calculations is we're able to work out the energy difference. So there's about 0.44 electron volts per unit cell difference in energy. So the ferromagnetic state is lower by that amount than the paramagnetic state. Okay, so overall that's why the system, in moving from that initial paramagnetic state in which the electrons are paired, if it goes down into the ferromagnetic state, it can gain 0.44 eV per unit cell. That's quite a reasonable amount of energy, and so that is why iron is in its ground state, wants to be ferromagnetic. Okay. So just to say, these are DFT code calculations done with a code called CASTEP that's developed here in Oxford, as well as a few other universities, and you'll learn how to do these calculations in the third year. So I just want to loop back now to the first lecture, and in that first lecture I talked about the Einstein-Den Haas effect. Okay, and that was where we had a rod cylinder of a magnet suspended by a wire. Okay, and we put this in a solenoid, and the solenoid was able to change the magnetization of the sample. And for example, if we thought about this, Einstein thought about this in terms of something actually going round in a loop. Okay, so it has, in this case, it has angular momentum going this way, and if we were to change the direction of the direction of travel, we would oops, sorry, that way. We would change the direction of the angular momentum. And so if magnetic moments are directly linked to angular momentum, then if we're changing the magnetism of this sample, we would see a change to conserve angular momentum. We would see a rotation of the of this cylinder. Okay, and that's what Einstein saw with Den Haas. And so he concluded that magnetism was related to angular momentum, and in that sense he was right. But I said at the time that Einstein missed something. What Einstein missed was that the magnetic moment is related to a constant, the Bohr magneton, times J, the angular momentum. But what wasn't known at the time is that we need a G, we need the G factor in there. Okay. And at the time, 1907, Einstein thought that the magnetism in the, he had an iron sample, so he thought the magnetism that he was seeing was due to electrons going round in orbits. Okay, and so if it's orbital angular momentum, G is equal to 1. Okay, but we know he was looking at iron, and we've just seen on the previous slide that the magnetism of iron is almost completely coming from the spin of the electrons. And for spin angular momentum, the G factor is equal to 2. So if these experiments had been done more carefully, what would have been noticed is that there was an unexpected factor of 2 between the magnetic moment and the angular momentum. Okay, but I mean, it was very difficult to do those experiments, and so they just took the idea that there was a change in angular momentum. That they saw this thing rotate, this cylinder rotate. They just took that as an indication the experiment had worked. But later, when people were able to do this experiment much more carefully, if you do it for iron, you'll need to take into account this factor of 2 because of the fact that it's spin angular momentum. Okay, I think that's kind of nice because spin is this quite we say spin is something that doesn't have a classical analog. We know what orbital angular momentum is because it's the same angular momentum as spinning on a desk chair, but we don't know what spin. We don't have a model for what spin really is. We just know it's a type of angular momentum, and this type of experiment on something like iron shows you that spin is indeed an angular momentum in the sense that it has to obey the conservation law that angular momentum does. Okay. Now, actually, these types of experiments can be quite interesting because, okay, in BCC iron, the magnetism is pretty much coming from the spin. But if we were to go and look at a ferry magnet, for example, containing a 4F metal, something like nib, for example, neodymium iron boron magnets, very common, quite strong magnets, or the samarium cobalt magnets that you often get in headphones. We would find that the magnetism there is coming from a mixture of orbital and spin. And so we would do this, you could do this type of experiment and calculate the G factor. It won't be 1 or 2, it will be the Landé G factor that we earlier derived, 6/7 or some number between some other non-integer number. But this type of experiment would enable us to find out how much of the magnetism is due to spin and how much is due to orbital angular momentum. Okay. So this last slide, just to emphasize, the Einstein-Den Haas experiment is non-examinable. I have just mentioned it because I think it's kind of interesting.